this next demo, we don't really need to concern ourselves with the sparks. So I'm going to zoom out a little bit here. And with a cell phone that really doesn't like zooming nice and smoothly. And what we're after this time is I want you to watch the behavior of the small sphere. So ignore the sparks, ignore the volume. All I want you to do is watch what this sphere does when it's sitting like this. So pay attention just to its behavior. Did you see that motion? It rocks as the machine's firing. And you get this motion going on. See if you can correlate the motion with the sound of the spark. Now the wobbling gets a little bit out of control, but if you hold this while it's on, you can feel a pull that disappears the moment the spark fires, or it hits me in the nose. It leans, snap, relaxes. Leans, snap, you hear the snap, and it relaxes. So it's pulled towards the dome until it sparks, then it suddenly falls back. If you were to come in and hold this, you can feel that pull. Particularly if you hold it in your open hand like this, you can definitely feel this attraction, relax. Attraction, relax. How can we explain that? What would cause the dome to want to be attracted towards each other at first? Well, this is one charge, this is another. What do opposites do? They attract. What happens at the moment of the snap? Okay, they discharged. So now they're neutral. There's no shock to be had. So they lean towards each other when they were attracted. And depending how you set this up, you can get a lot of bouncing around. What this would mean is if this machine was big enough, it should be able to physically pull the other ball right towards it. So let's see what happens if I do this. Just try right here. Owie, 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 owie. Oh, it's attracted to me. Let's see. Doesn't seem to be working yet. But it's strange, there should be an attraction there. It's attracted to me. We have to figure this one out. Whoa, right on the nose. Okay, so what we're seeing is attraction, relax. Attraction, relax. This is how the first alarm bell was made. Ben Franklin did this, and he did it in a lightning storm, and the little ball was going bang, 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 and he could wake his family up to say, look at the lightning I've piped into the house. He was a very lucky man. Now we've got the classic effect to look at. The one that everybody's looking forward to, putting their hand on the Van de Graaff, getting their hair to stand on end. But there's a reason I can't demonstrate that one for you. But what we were able to see is there's a lot more to this machine than what you think, okay? So we were able to determine the polarity of the machine, rough idea of its voltage, explain the rate of the sparks versus distance, the level of sound versus the distance, and the level of shock. And if you are so bold as you want to touch an operating Van de Graaff, the trick is not to dangle around way out here, it's to get in quick so the voltage can't build up. The final part then would explain why this distance here is critical to the operation of the machine. Because this gap, if it's 1,000 volts a centimeter, if this machine exceeds that voltage that's between here and the ground, the sparks will start jumping downwards to the table. So the taller the Van de Graaff, the more oomph it can reach before it finally fires a spark. If I remove this little dome, the sparks will go straight downwards along the belt into the box of the machine, which doesn't really harm the machine, but it sets fire to the belt. So the vertical height of the Van de Graaff is not just for display purposes. The taller the column, the more voltage it can reach.